Okay, I just want to return to our unit goals to make sure you understand how far we've come. Our first big picture goal was to describe the chemical principles behind how enzymes select a particular substrate. That's really the idea of specificity. Second, understand how enzymes make reactions go faster. That's catalysis. All we have left to do is interpret kinetic plots. Just a few words, but it's actually some very difficult and long material that we've got to cover. So let's go ahead and get to that material. Let's move ahead to some new notes and begin our discussion of enzyme kinetics. What is this all about? What's the word kinetics? This means measuring reaction rates. This is something that biochemists do. You're going to do it in the lab if we have the chance to be in the lab. We'll certainly cover it in the lab. But it all has to do with this idea that enzymes speed up reactions. And if we can measure them, we can understand a lot about the enzymes. So let's talk about how enzyme kinetics are measured. We're going to carry out what's called an enzyme assay. Assay is just a fancy way of saying a test or a measurement. And what I'd like to do is do a little bit of a thought experiment and run an enzyme assay for you. What we're going to do is measure the concentration of product at any particular time, let's say in a test tube. And we're going to do that as a function of time. So remember, substrates get turned into product. And what we can say for sure is that at time 0, if you start with enzyme and substrate, you're going to have 0 product at the beginning. So let's start over here. We have enzyme and substrate added, and we have no product, so we have 0 product at time 0. Now, let's just say what would happen if we just added substrate and no enzyme. Well, we already told you that without enzymes, most substrates are going to not turn into product at any appreciable rate. So let's make a note of that. This is going to be in the absence of enzyme. We get nothing. You just have substrate and no product being formed over time. Okay, but let's say we do put some enzyme in and let it interact with the substrate. We certainly start with no product at the beginning, but after some time we measure how much product is there, and we have some. We keep measuring it, and it goes like this, and eventually it levels off like that. So let's say that this is in the presence of some amount of enzyme. We would see data that looks like the top curve. Now, here's a question for you to ponder. Pause for a minute and let's think about this question. When we add enzyme to substrate, the substrate becomes product over time, but it eventually levels off. Why does it level off? Pause for a second, see if you can come up with that. Okay, the answer to that question, why does it level off, is because we run out of substrate. We're cruising along, chewing up substrate, but eventually it gets slower and slower because there's not as much substrate to bump into the enzyme. Eventually you run out, and that's the end of it. What I want to do is focus back here at the beginning of the reaction. That's when there's lots of substrate, very little product at the beginning, and what we have right there is the slope. That's what's called V sub naught. All right, what the heck is that? Let's talk about V sub naught over here. V sub naught is what we call the initial velocity. We are measuring rates here, and a velocity is a rate. Well, what is the velocity? The velocity is the change in product concentration as a function of the change in time. Isn't that rise over run? Isn't that just the slope? So the initial velocity is the slope of the reaction very early, at time zero, we even would say. That's what the naught means. That means the velocity at time zero. Now, that's the rate of the reaction that we are really interested in. We're not really interested in what happens out here after things start to peter out. We're really interested in what happens here at the beginning when the slope is linear, not after it starts curving. Okay, so far so good. Why are we interested in the initial velocity? Well, here's why. We're going to give you lots of examples. We can use this initial velocity as a test of how the enzyme works under various conditions. Let's give you a few examples down here. For instance, we could test the enzyme and its substrate, measure that velocity under a bunch of different conditions. For instance, we could choose to measure it at various pH levels from 0 to 14, let's say. Let's say we did a whole bunch of different reactions, like we showed you over there, and we measure the velocity, and we plot those initial velocities out like that. What you can see is that for this particular example, at pH 0 and pH 14, there's almost no activity. It would be basically a flat slope from that curve above. And at pH 7, right in the middle, you've got a very strong activity. And everywhere in between, it's sort of an in-between velocity. We have a nice bell curve here, and this is what we call a pH profile. And we can learn a lot about enzymes from pH profiles. We could do the same thing, that is, measure velocity as a function of other things like temperature. Maybe we could measure it at 0 degrees Celsius and 100 degrees Celsius. Well, again, we'd see very poor activity at the extremes and very strong activity at some point in the middle. Maybe this would be something like 37 degrees Celsius. That, by the way, is the temperature of the human body. We can learn a lot about enzymes from a temperature profile. There's one really interesting thing about enzymes that's worth noting. Enzymes usually have maximal activity, their peak activity, in the conditions in which they are normally found. Doesn't that make sense? If you have the enzyme chymotrypsin, it works in the intestine, which has a pH that is pretty neutral. So you would expect it to work really well at the neutral pH. And it works in the human body, so you'd expect it to have maximal activity at 37 degrees Celsius. There are other examples, by the way. I'll show you just a counterexample. What if you had an enzyme that was found in a very alkaline lake or something like that? Well, maybe its activity would be peaking at pH 10 or something like that. And so you might have a different profile like that. So again, we can learn a lot from these types of profiles, but none of these are the most useful thing we can use for velocity. And that's going to be in the next video when we measure velocity and plot it out as a function of substrate concentration.